Okay, people were getting a little bit confused about when to use what equations, so let me just write out all of our equations. So first of all, we have our FG is G M1 M2 over R squared. This one is on the equation sheet. This is for talking about the force of gravity, or the gravitational force, or also aka weight. Weight also means Fg. So that's the instance when I would use this equation right here. The other thing is G. On your equation sheet it says little g equals Fg over m. Now, using Fg over m isn't super helpful if you don't know like what the Fg is, but we just said right here, so this is what it looks like on your equation sheet. We just said right here that Fg is G M1 M2 over R squared, so if little g is just this equation divided by m, that's just taking out one m. So then little g is G M over R squared. So this one's given, this is what's given, but you kind of want it to look like this, so it's a pretty easy transfer to here. What this is talking about is it almost always calls it the gravitational field strength. And that also could be the acceleration due to gravity. So like on Earth, little g is 10. That is the gravitational field strength of Earth. It is also the acceleration due to gravity when you're like right on the surface of the Earth. Orbital velocity. So this is when you have something in orbit, the only going around in, wow, that's not a circle. The only force acting on it is gravity, so your centripetal force is force of gravity, mv squared over r equals gmm over r squared. One mass cancels, one r cancels, so v is the square root of gm over r. This is not given to you on your equation sheet. I would memorize this. For multiple choice, right, that didn't take me long, but it did take me some time, right? You'd have to be like, oh yeah, this is the only force, centripetal is my gravity, get v by itself. If you have this memorized, then when you get those questions, it's like, satellite A is orbiting at an orbital distance of blah, blah, blah. You can just go, oh, that's 5 times r, and find the velocity, etc. Super, super important to note. One of the mass canceled, this mass that's left, this is the mass of the center object. Whether it's a planet or a star or whatever, it doesn't matter. Whatever the center object is this mass right here. This mass, the satellite mass, or the thing that is actually going in a circle, canceled out. So it does not affect the velocity. And then lastly, period, you would use that period is just 2 pi r over the velocity because it equals d over t, and your distance is just the circle, 2 pi r. Those are all my planet gravity equations. Now for circular motion, you could very easily have something where it's like, I have tension in the center. In that case, my centripetal force is tension. You need to know that centripetal force is, so I'm going to write off to your side, centripetal acceleration is v squared over r. This is on your equation sheet. What is not on your equation sheet is centripetal force. But if you have a centripetal acceleration, well, force is just mass times acceleration, so it's mass times v squared over r. So you need to know this one as well. I think that's all of your equations. Yeah. So, for number 1, a child rolls a ball around the end of the rope in uniform circular motion, so something like this, ball going around. Which of the following statements is not true? Uniform circular motion, it would have a constant speed. Your velocity would not be constant. Velocity includes direction, and the velocity's direction is definitely changing. It'd be like this, and then here your velocity, and then here's your velocity, and then here's your velocity. So velocity is actually changing because its direction is changing. Radius would stay the same, and the magnitude of the acceleration would be constant. Magnitude meaning not direction, because the direction of the acceleration absolutely changes. It's pointing to the center at all times. Equilibrium, meaning balance forces are not accelerating. It's tempting to put A because this is constant speed, but because it is changing directions, it technically does have an acceleration of v squared over r. Cart rolling down a frictionless incline, frictionless and rolling down would for sure accelerate. Free fall definitely accelerates with g, and then sliding at a constant velocity, that one is an equilibrium. A stone of mass m is attached to a strong string and whirled around in a vertical circle of radius r. So looks something like this. At the top of the path, the tension in the string is 3 times the stone's weight. So tension is T equals 3 times the stone's weight. Well, weight is just the force of gravity. In this case, the force of gravity would just be mg. So tension is 3 mg. I'm asking for the stone's speed. We would not use v squared of gm over r because that is specifically for like an object orbiting another object. I'm twirling something around on a string. That is not an orbit, it just happens to go in a circle. So here I want to draw my free body diagram. I've got the force of gravity pointing down because we're talking about something whirling around in a circle, right? Not something out in outer space. So if I do this standing in my classroom, the gravity will always point down. And then tension will also point down at this point because the string is pulling into the center. So then because this is moving in a circle, it's like writing a net force equation, but it's an FC equation for going in a circle. And these two would combine to make my centripetal force, so it would be Fg plus tension. And then now we just replace, Fg would just be mg. I do not need to use gm1m2 over r squared because I'm just on the Earth. It's just mass times 10, or g, little g. And then tension we said was 3 mg. Centripetal force is always mv squared over r. Mg plus 3 mg is 4 mg. And I'm looking, oh, that's an m. I'm looking for velocity, so I'm going to multiply my r up. I'm going to divide my mass over. That cancels, so then velocity is square root of 4gr. None of my answer choices are that. That doesn't mean we did it wrong. Let's look. Square root of 4 is just 2. And then g and r have to stay in the square root because they are not perfect squares. They can't come out, so it's a. Writing the equation for orbital velocity, so that's what we wrote over here. So that is v is the square root of gm over r. The thing that we want, only thing that depends on is the mass of the center thing, whatever it is, the planet, sun, doesn't matter, and the orbital radius. So how far, let's think if this is my picture, I need this mass right here, this mass totally irrelevant, and I need the orbital radius, the distance from here to the center to the center. That's my r right there. Again, this mass totally irrelevant when we're talking about the velocity. Only mass that matters is the center one. Weight. Weight is just another name for force of gravity. The force of gravity equation is this one right here. Or you can use Fg is mg. That's like on the Earth basically because you know g for Earth. So if you're zoomed out, if you're not on the Earth, you want to use this one. Gravitational field strength is talking about little g. That's also called acceleration due to gravity. And this one we already wrote on the other, at the beginning of the video, is just Fg over m. So just take out the second m. So this is gm over r squared. How I think about this is the force of gravity, or the weight. So if I have an apple on the Earth, right, the weight of the apple and the mass of the apple absolutely matters. If I'm talking about the acceleration due to gravity on Earth, that my apple is going to fall out, the mass of my apple has nothing to do with Earth's gravitational field strength, right? The mass of the Earth matters, not the mass of my apple. But for the force of gravity force between them, now the second mass matters. Which of the following would increase the gravitational field strength of an object? So that is gm over r squared. So I want to increase the gravitational field strength of some planet or something. Of a planet. So I can increase the mass and I can decrease r. Now you see two increased masses. There's only one mass in the equation, so think about what would affect the gravitational field strength of the planet. The object's mass or the planet's mass? Hopefully you said planet's mass. And then I can divide by a smaller r. That would give me a bigger little g. So then a smaller r decrease the separation distance d. Alright, I've got satellite A and B. It says that B is 3 times more massive than A. So I'm going to call that one M and this one 3M. And it's orbiting at 3 times the distance. So that's already on here, D versus 3D. The gravitational force between A and the planet is F. And I want to know what's the force between the planet and B. So it has a greater mass, but it's also farther away. So I'm going to look F equals G M1 M2 over R squared. So that's my original. Now I'm saying, okay, 3 times the mass, so this is G3M over 3 times the radius. Careful, radius gets squared. See how that would be 3 over 9, or times 1/3 smaller force? Well, the old force is F, right, because we're comparing it to just M and D, so then that's 1/3 the old force. Satellite A orbits at a speed of V. What is the speed of satellite B? So first of all, satellite speed, that's talking about orbit, so this is square root of GM over R. Now, I know my radius is 3 times greater, and you might be tempted to say my mass is 3 times greater, but think about, I only have one mass in this equation. We know that for the orbital velocity, it's the mass of the center object that matters. The mass of the planet is not 3 times greater for this satellite because this satellite. The mass of the satellite actually cancels out in this one, right? I don't have the second m, so I'm actually going to keep the same m, right? The mass of the thing in the center has not changed. So then now, this is my original. My new one just has a factor of 3. Notice it's on the bottom. It's also in the square root, so that's a factor of 1/3, which is just 1 over root 3 times the old velocity, so F. Old velocity over root 3. Right, it says that spacecraft X has twice the mass of spacecraft Y. They orbit Earth at the same radius, which of the following must be true. So it's helpful to draw a picture. They're both at the same radius. This one, X has a mass m, and Y has a mass 2m. Oh no, Y has a mass of 2m. Because it said X has twice the mass. Ooh. X has twice the mass of it. This one. Okay, anyway. Which of the following is true? X feels a greater gravitational force. So think about gravitational force is this equation right here. Both masses matter, so if one had double the mass, then yeah, that would be a greater force. So A is definitely true. Twice as fast. Fast is velocity, orbital velocity, because we're talking about things orbiting around, so that's square root of GM over R. Think about only one mass matters, and it's the mass of the center object. So if this one had a greater mass here, that does not mean faster, because the mass is of the Earth that we care about for this equation. It's the same Earth, so same mass, so then that's not true. They would have the same V. The period, so period is just 2 pi r over the velocity. We just said they have the same velocity. They're at the same orbit, so they'll have the same r. So then they'll have the same period, so D. It does not take twice as long. They have the same period. It takes the same amount of time, A and D. On a planet with triple the radius and quadruple the mass, the gravitational field strength, so let's talk about little g. Little g is gm over r squared. Now I want to triple the radius and quadruple the mass, so that's going to be times 4/9 smaller. Now sometimes I ask just like, what is the factor different? Here I didn't ask that. I want to know what is the gravitational field strength on this planet. Well, look at what I'm comparing it to. I know it's 4/9 smaller, 4/9 smaller than Earth, right? Because I gave you the mass and the distance in terms of the Earth's mass and distance. So it's 4/9 smaller than Earth's gravitational field strength. We know Earth's gravitational field strength is just 10, so it's just 4/9 of 10, which gives you 4.44. Planet X has twice the mass, but half the acceleration due to gravity, so we're talking about little g. So I'm going to say 2m. I want to know what's happening to the radius, and I want to end up with times 1/2, because I have half the acceleration due to gravity. Right now I've got a 2 on top. To get to 1/2, I need a 4 on bottom. So what I need to do to r is I need to multiply by 2, because it's going to get squared. So I just want twice the radius. And then if you're ever unsure, just check. Okay, I have 2m, I've got twice the radius. That's times 2 over 4. Yep, that would give me 1/2 the acceleration due to gravity, so I'm right. A planet has 3 times the radius and 3 times the mass. What is the acceleration due to gravity? So now 3m, 3r, 9 times the mass, sorry. So that would be 9 over 9, which is times 1, which means it stays the same. I didn't ask what happened. I want to know what is the acceleration due to gravity on this planet. I know it's the same as Earth's, and Earth's is 10. So your answer is 10. 2 planets have the same surface gravity. This is my bad. I meant to go back and change this to gravitational field strength, blah, blah, blah. So this is just saying little g. Pretend that had said gravitational field strength. So same little g, but planet B has twice the mass of planet A, so I want to know what happened to its radius. So 2m, what happens to r in order to end up with the same. So same would be if I have a 2 on top, I need a 2 on bottom. But I don't want to double the radius because that would give me a 4 on bottom. What I need is root 2. Because when I square root 2, that's going to give me 2. So root 2r, and then just double check. 2m over root 2r squared, that's 2. Root 2 squared is 2. That would be 1, which ends up the same. If I want to determine the orbital period of a satellite, and I know the mass of the planet and the radius of the planet that the satellite is orbiting, and do I have enough to calculate period? So let's think about, period would just be 2 pi r over v. So I would need velocity, but velocity, if you're talking about orbiting, is just gm over r. So, as long as I have m, assume we know g, the constant, right? As long as I have m and r, then I'm good, but I just need to make sure I have an m and an r. Is it the right m? Is it the right r? So think about, if we have a planet and the satellite, we care about the mass of the planet. So that is the mass of the planet, so I've checked off here. Now the radius, I have the radius of the planet. The radius of the planet is not the radius of the orbit. See how the radius of the planet is only part of the radius? I need all the way out to the orbital radius. So what I would need is the height above the surface. So is there anything else? Yes, you need the height above the surface. Right? The orbital radius is not going to be the radius of the planet unless you're just orbiting at the surface, in which case you're not orbiting, right? You're just standing on the surface going around in a circle. That's different. 2 identical planets orbit a star in concentric circles. Of the 2, the planet that is farther away must have, so here's my star. I've got 2 planets orbiting, one is farther away. The one that is farther away, so think about the thing that is different is it has a bigger r. It has a bigger period, smaller period, velocity, acceleration, and gravitational constant. So first of all, gravitational constant is a constant. It's not going to change because I went farther away, so you can cross off this one. Gravitational acceleration is the little g equation. Orbital velocity is square root of gm over r, and then orbital period is 2 pi r over velocity. So a bigger r would actually mean a greater period, right? Direct relationship, so not that. A bigger r, you'd be dividing by a bigger r, which made a less velocity, so slower velocity, that is true. Larger acceleration, actually you're dividing by a bigger number, it'd be less acceleration, so B is the only true one. Radius of Mars is 1/10 that of the Earth, so 1/10 r, and, 1/2. And the mass is 1/10 the mass of Earth, which the following is the gravitational field strength, so that is little g. Gm over r squared, but now I'm plugging in 1/10 the mass and 1/2 the radius. So what you want to plug into your calculator is just 1/10 over 1/2 squared, and make sure you put in parentheses. That's going to give you times 0.4. Now that is not the answer, right? That's how many times smaller the acceleration or the gravitational field strength on Mars is compared to Earth's. And we know Earth's, right? It's 0.4 smaller than Earth's, which is just 10, so then on Mars is 4. Satellite B has 3 times the mass of satellite A, which has a faster speed, so velocity is square root of gm over r, but that's the mass of the Earth that I would plug in here, not the mass of the satellite, so it should be the same mass, same speed, which experiences a greater centripetal acceleration, so v squared over r. Well, we just said that this is the same. They definitely are at the same radius, so then they'll have the same acceleration. You also can think about the acceleration as, in this case, right, the centripetal force is the gravitational force, so the centripetal acceleration is the gravitational acceleration, in which case the only mass that matters is Earth, not the second mass. Gravitational force is different. It has both masses in the equation, so they do have different forces, and the one with the greater mass will have a greater force of gravity, so that would be B, because the second mass matters now. Hypothetical planet has a mass 8 times that of the Earth and twice the gravitational field strength, so that means twice the G. So I want to end up with times 2, and I'm looking for what, how many times greater or smaller Earth is. So if we look here, I've got 8 on top. To get to 2, I need to divide by 4, so that means I need a 2 right here, because 2 squared. So that would give me 8 over 2 squared. 8 over 4 is 2, so that's good. So I need twice the radius. Hypothetical planet has a mass half that of Earth's and 8 times the gravitational field strength, so 8g, so I need to end up with 8, and I'm looking for what happens to R. Now here, you have 1/2 and you're ending up with a bigger number, which means I'm not dividing by a regular number, I must be dividing by a fraction, because only dividing by a fraction do I end up getting bigger. If you divide by like whole numbers, right, you're going to get smaller. So let's think about, I have 1/2 right here. That means I need a factor of 16. I don't want to divide by 16 because that's just making me get smaller. I want to divide by 1/16 because that's going to be the same as if I just multiplied by 16 over 1. And see how 16 with the 1/2 would give me 8? So that means 1/16 is the factor I need on the bottom, which means I need 1/4 right here. And then just always double check. So I have 1/2 m over 1/4 r squared. 1/2 over 1/4 squared is going to give me 8. So that's my check. So your answer was 1/4 the radius. That's an R. Here we're back to something string on a, circle on a string, right? We're not in outer space. We're not talking about planets. So it's just on Earth, twirling something on a string. The mass of the sphere is m, the radius is r. The position, sketch the acceleration vector. So your acceleration should be pointing to the center at all points. Center, A. That's also my centripetal force. My velocity would be different. My velocity would be here, it'd be here, here, up, down here, etc. B got cut off on the printer, but B is over here. So free body diagram at point A. I know that, of course, I have gravity down because we're not in outer space, we're just on the Earth. Actually, I'm going to do that for all of them. Gravity down for all of them. Now, I also have the string, the tension in the string. So at point A, the string would be pulling up, and I know that my centripetal acceleration is up, so that means the tension must be greater. At B, the tension would be pointing straight to the center because the string is pulling it to the center. And C, the tension would be down, like this. Now I want to give an expression for the tension, so let's write. This is not a net force, it's a centripetal force. It's like a net force, but for specifically centripetal circular motion. So Fc here would be tension minus Fg. Fc here is just going to be the tension, and Fc here is both of them together, tension plus Fg. Now I'm going to get the T by itself, so that's Fc plus Mg, already by itself, and then this is Fg minus Fg, and then now we just replace. Fc is mv squared over r, mv squared over r equals tension, mv squared over r minus Fg, which is just mg here. I do not need to use gm1 m2 over r squared, because again, like, it's just a ball on the surface of the Earth, so it's just mg. It's not like different planets or zoomed way out in outer space. Alright, two objects orbit the same sun. The first object follows a circular path with radius r and has a velocity v. The second object orbits at a radius of 25 r. So this is my sun, star, whatever. This is the first object, and then the second object is like way farther out. This one has a radius of r and a velocity v. This guy, obviously not to scale, 25 the radius, and I want to know how fast is it going. So we're talking about speed, so that's orbital speed specifically, right, around only gravity acting on it. So if this is my orbital speed, the first guy has r. It's orbiting the same sun, so m stays the same, but now the second one has a radius of 25 r. And now we just pull out our factor. We've got a 25 on the bottom, but it's inside a square root, so that would just be 1/5. So it's 1/5 the original velocity, so that's v over 5. Two satellites, x with a mass of m and y with a mass of 2m, orbit the same planet at the same height. If the first guy has a velocity v, what's the orbital velocity of the second guy? So same planet, I've got m and 2m, bigger mass. Now velocity is square root of gm over r. They have the same r because it's set at the same height, and also they have the same m because the m here is the mass of the planet, not the mass of the satellite, so it doesn't matter, it's the same velocity. Mass of the satellite is irrelevant. lower altitude, lower height is a smaller r. So now we're looking at speed and period. So velocity is square root of gm over r. If I have a smaller r, that means a bigger velocity because it's an indirect relationship, so greater speed. We're between c and d. And then period is 2 pi r over v. I have a smaller r. I'm also dividing by a greater speed, so smaller divided by a bigger gives me smaller overall, for sure. 2 reasons it's getting smaller, because on top's getting smaller and on bottom's getting bigger. Here, careful you read. We're looking at the lowest point. The picture's at the top, but I'm asking about the lowest point, the velocity and the acceleration. So acceleration's easy. It goes to the center. And then velocity, you have to look. It's going around like this. So at this point, the velocity is to the right. So velocity to the right and A to the center is C for the lowest point. If this is a ball of mass m and it's swung in the circle, at the lowest point, what is the tension? So let's draw a free body diagram at the lowest point. You've of course got gravity, and then you've got tension pointing up, and tension is going to be greater because it's definitely accelerating upwards. So centripetal force is T minus mg. Add over. Centripetal plus mg equals tension. Now normally I would place this mv squared over r. But my answer doesn't have mv squared over r, so let's look. It does have mg plus mac, where ac is v squared over r, so you can just leave it like that. So then your answer is B. Coin of mass m is placed on a vinyl stereo record of radius r, moves at a constant speed. If the frictional force between them is at a max value, then which of the following can be used to find the coefficient of friction? So I'm looking for mu. We are talking about just something spinning around in a circle like this, right, some distance r away. This is my mass, whatever, coin. So we are not talking about like planets, right? We're not talking about orbital velocity. This is just the velocity of something spinning. Draw your free body diagram. We've got Fg, and we've got normal force because it's sitting on this stereo record, not falling down. And then the force that is keeping it going in the center is the friction force, holding it like stuck to the plate, kind of. Then the force that is serving as your centripetal force is the friction force. Friction is mu Fn, centripetal is mv squared over r. My Fg here, because we're just on the planet, right, on Earth, that's just going to be mg. So I have mu mg, because normal would just be balanced out, equals mv squared over r. M's divide the g over. So then mu is just v squared over rg, which is d, grrg. And what happens if the record moves faster than this speed? So this is saying the friction force is at its maximum value. If I go any faster, what's going to happen is that my friction force, right, if it's already at its max value, it's not going to be able to be enough to keep the centripetal force. So because the F of friction is not enough to like be the FC at a faster speed, the coin will slip off. The friction force will not be enough to keep it going in a circle if you go too fast, so then what will happen is it just slides off. It won't continue in a circle.